Yes, good morning and welcome back. So, we are introduce certain compact embedding, especially the last theorem of H1 of omega contained in L2 of omega for omega bounded will be used immediately during the weak formulation from the. So, we will have one more theorem state relic contraction. Yeah, it is important that you should go through these proofs in our previous course. Let omega subset of Rn bounded open, these are more general results. Then 1 for p less than n, we already made this comment W1p of omega compactly contained in and of course we also assume smooth in LQ of omega for all 1 less than or equal to q, p less than p less than or equal to q less than p star. I already commented you do not get compactness for the case when p equal to 2. When 2 p equal to n, that is W1n of omega, which is the direction you have, and at infinity you have LQ of omega for all p, for all q, in n to infinity. Of course, at infinity you do not even have the continuous embedding, so you cannot expect the compact embedding. Okay, 3 when p greater than n, and you have W1p of omega compactly embedded in C of omega bar. So, you get it. So, the non-trivial part of the proof is only for 1, and the proof for 2 can be easily deduced from the proof for 1. So, that is not difficult, you just use it and you can get that. So, what do you do for proof of 1 is non-trivial? So, we do not make any comments, trivial. 2 follows from 1. So, how do you do that? You just choose some epsilon positive and small, and then W1n of epsilon you can omega is contained in W1 n minus epsilon of omega, that you know, and then this one n minus epsilon is strictly less than n, and you can apply the part 1 to get this compactly contained in LQ for all q less than p less than n minus epsilon star, and then you can see that epsilon goes to 0, this goes to infinity as and then epsilon goes to 0, and you can actually get that one. The third one is a kind of a classical result. How do you get compactly embedding? How do you get relatively compact set? To get a relatively compact set here, you prove EQ continuity and boundedness. So, 3 can be again proved in a straight. So, the part of 1 is a non-trivial case. So, to prove 1 it is much more complicated. I say I do not have time even to comment here. So, basically what you do is that you look for how to, just like in C of omega bar you have this C of omega bar, you look for EQ continuity, and so there is a characterization how to say a set is relatively compact. Similarly, you have to first prove a certain result. How do you get it? This is already done probably in the we have seen these such things in our part 1 of this course, the characterization of compact sets in LQ of omega. So, let me not recall such things here. So, let me go to the final part of this thing before variation of formulation, inequalities. I want to prove one important inequality. So, I do not know I will have time, but let me state first and then we will do that one. The first important thing we will be immediately using is Poincare inequality. Okay. What is Poincare inequality? So, omega bounded open set in Rn, open set in Rn. The proof is quite easy here, and then there exists a constant C equal to that depends on C and P such that norm of gradient of U at PLP is less than or equal to constant into norm of gradient of U at LP for all U in W1P0. Of course, this result will not be true for W1P because of the constant functions. Okay. So, this implies this also implies as a corollary U going to grade U at P is an equivalent norm, which will be using in the existence theory in W1P not of omega. So, immediately this the L2 LP or L2 estimates can be estimated by that way. Okay. So, the proof of this is pretty easy. Say for example, the easiest way of doing is that if omega is minus a to a, and then it is easy. So, suppose you have this omega like this, okay, and you know that it is 0 here, U is 0 here, this is your omega, okay. So, U is 0 here. So, you can write down any U x here. So, this we consider as x prime, this is your xn, then I can write down x prime xn as an integral of its derivative, that is all, and then integrate by parts. So, you can for every x in omega, I can write it as U of x is equal to integral minus a, it is 0 here, you see. So, minus a to xn dn of u x prime x dn of u x prime of t dt, and then you can immediately estimate modulus of, you can even get the constant estimate, it will be something like a diameter. So, you will have 2a power p by q, apply the Helder inequality to get integral minus it's a bigger number. So, I am taking the modulus dn of u power p, this you are integrating with respect to the last variable, that is equal to dxn if you want it, you can write over 1 over p. Now, again integrate, okay, integrate with respect to you power it and integrate with respect to x dx x fully, and already xn integration is done. So, you get some constants etc., and which will eventually will lead your norm of ux at LP is, you power it with respect to p and then you integrate, okay. P less than or equal to, and the constant depends on basically the diameter. It depends only on A, constant into, you work out such details LP. For general omega, what is that, if you have a other omega, what you can do is that you can always if you have a bounded domain omega, you can always find a rectangle contained here, and then u is 0 here now. See, you see u is 0 here. What? So you extend by 0 u tilde, u tilde is 0 here. So you extend by 0 here, and then you get to for estimate for u tilde, and u tilde is 0 outside. So using this argument you can actually prove immediately. So let me note x here. Okay. So you can immediately prove that u at LP is less than or equal to m of grade u at. Very, very important inequality. So you should not forget it, this Poincare inequality. So I want to make some remarks, and which is also exercises. Okay, so don't forget all these. The inequality is true. You don't need u to be 0 in the entire gamma. The inequality, you can prove this. So I will only make inequality is true on the space set of all u in W1 P of omega. All these factors you can use to study various boundary conditions, and the trace value is 0 on gamma and naught. So what you are basically doing is that you are having a domain omega, and you are dividing this domain, say gamma naught. So this may be your gamma naught. Only thing, it should be not almost everywhere. So it should be 0. So even if it is a small boundary, if the trace value is 0, you have your thing. Okay. Gamma naught can be anything with something like a non-trivial measure. So the inequality is not true in the inequality is not true in H1 or that mean matter W1 P of omega. Of course, we are assuming omega is bounded, but as the constant function u equal to c is, say, in H1 of omega. So it implies the grade u is 0, right? So it cannot be true in that one. The interesting point is that these constants are the only troubling terms. So if you can make an equivalence class, and if you can quotient space, you are eventually get inequality. So the trouble is the constant. The trouble is exactly the constant functions. Trouble is exactly the constant functions. We will discuss this more general theorem, and in fact Poincare inequality is true in the quotient space in, so you quotient it out. I will tell you how to define for more general case. I will make a theorem for the more general case. Okay. So I want to state one interesting things, one more theorem, which will be a corollary to a more general theorem. I don't know, I will get time to prove it, but and let us see. So, before Poincare inequality, let me do something, some more comments. So, this is anyway the comment thing, and you got it. Okay. So, you can iterate this process. So, one more comment, iterate the process to show that you going to, so you need only the highest order derivative sigma norm of d alpha of u at LP with mod alpha only equal to m is an equivalent norm. So, you have the basically you have the Poincare inequality with the highest derivative. So, the basically it is an equivalent norm means the highest order derivative works a norm there or can be estimated from below by the general norm. So, the estimating from below is the important thing. So, basically grade u you estimated in terms of u. So, if you look at the second order, so second order derivatives you want to estimate from below by the derivatives, other derivatives can be. So, the lower order derivatives has to be estimated in terms of the highest order derivative is an equivalent norm in W MP not of omega. So, you see. So, these things you have to, we may use it if you have time to study. Now, let me state the Poincare inequality. So, what happens is exactly something like I am doing it in a slightly different way of the quotient space, and later you will see the full quotient space. In a WMP of omega, we are going to define the quotient space. Okay. Let omega bounded open 1 less than or equal to p the infinity, then this Poincare Poincare is already done, Poincare Vertinger inequality. Okay, so, we are doing a Poincare. Then there exists C positive such that, as I said, it is the only troubling terms in H1 are the constant terms. So, you have to somehow remove certain constants from that one, okay, or you have to find with appropriate constant. So, you are removing a constant u bar. I will tell you what is constant, less than or equal to norm u at grade u at p, where okay, u bar is the average 1 over modulus of omega. You can take even the average on the boundary. So, let me do that one. You have to remove that. You will see soon that kind of thing. The average of u. You can take the boundary averages as well. Average of u in omega. So, you can remove that average constant and then you get this one. And further is also there. If p is less than n, so you get norm u minus u bar at p star is less than or equal to constant in. Okay. So, this theorem will be a corollary to a general theorem, and that is what the theorem which we are going to. So, let me I do not know whether I can prove result, I may not have the time. So, let us see, first let us this thing. So, proof you can read it from the book, that would be good. So, I want to see this space W m plus 1 p omega, okay. And so, omega as usual is a bounded open set, and Pm of omega space of polynomials of degree space of polynomials of degree in omega n variable, degree less than or equal to m. Okay. So, what we are going to see the quotient space x equal to w m plus 1 p and quotienting out by all polynomials by degree omega. And of course, when m equal to 0, this is W1P and your P0 is nothing but constants. So, that is identified with a real line. So, you have your this space. Okay. So, that is what we do it. Okay. So, you have this quotient space and what is your equivalence relation there? U equivalent to V if u minus v is a polynomial of degree less than or equal to m, is in degree m. Okay. So, this is according to that you will have your equivalence class u. Okay. So, you have your equivalence class and any two elements in a equivalence class is differ by a polynomial of degree m. That is what you mean it. Okay. Then you can define a norm. So, you are somehow you are looking for the best norm possible. Okay. So, in an equivalence class, if it is in this case here, if you are taking two elements here v u, then u minus v is a constant. That is the equivalence relation here. So, among that you are looking for the best norm in an infimum you are telling. So, you are looking for all the norms in that equivalence class and looking for the best one, infimum. So, that way, so how do you define a norm? So, you can define a norm. So, on X of this equivalence class this norm is defined on X is looking at it infimum norm of v plus p, instead of constant there you are looking for all the polynomials is an m plus 1 p norm, m plus 1 p, and for all p in p, that is what you are doing. If you look at it here you will get that norm of v, the difference any two vector you are looking at it x space, x is this one, is nothing but you are looking at infimum or v plus c, you see, for all c in Rn. So, that is why, so you are somehow you are choosing the least norm among all by adding constant, which constant gives you the best. Okay. And this norm is equivalent. So, the theorem is basically, theorem is the above norm is equivalent to the highest norm, which I think so equivalent to v m plus 1 p, this by definition summation norm of d power alpha of v at p, and you are summing over all m plus 1. See, on the n plus 1 variable, when you add a polynomial of degree m, the m plus 1 derivative of that vanishes. So, it is the material which v from that equivalence class you take it, irrespective of whichever v you take it, the contribution from the highest order derivative does not come, and it is a bit of an analysis, prove some contradiction argument. You are basically to prove, you have to show that so the norm you should be able to estimate. This is what basically you want to prove it, constant into v at m plus 1 p and then some constant prime into norm of v at m plus 1 p. Okay. And this part is obvious, that is because this is a bigger term, so it comes with the same constant, that is not a problem. But this portion, so you see all your other derivatives can be estimated by that. Okay. So let me not give the proof because I do not have the time, because I want to do something. Okay. So at least let me define the so I want to define one more interesting thing, which is an application to what are called the interpolation error as a corollary. So the numerical analysts use this, what are called an interpolation estimate. That is why the one reason to state this at the end of it after Sobolev spaces interpolation. Let V be a Banach space. Containing W is a bigger, that is what interpolation you do. In numerics, when you want to look for a solution in this space, you will interpolate and interpolate that functions in a bigger space. And pi is the interpolation, pi from W m plus 1 p of omega to V. So it's you are making for the taking elements from W1 p of omega, do some finite element or finite difference method and construct functions which will be something like here it will be H1 space, that will be a kind of an L2 space, something like that one. Continuous, linear, and it fixes PM element. That means when you have a polynomial, many of these tricks will study even when you do a numerical approximation, deriving numerics computations for the integral. You construct various numerical schemes, many methods by on a certain order of polynomial it will be exact. So that is what we are exactly doing it. P, this should be for all P in or P in P. You see it fixes the polynomial P, and then this is the interpolation. Then there exists a constant C positive such that you have an interpolation. So you can see that the U is your solution, pi is your interpolation thing, and its error, this is basically an error. Error is estimated in V, because pi of U is in V is less than or equal to constant into summation of U at m plus 1 p, of course with the not full m plus 1 p. So sorry, only the highest order derivatives are calculated. That is the whole idea, right? Constant into U at m plus 1 p. So the proof is trivial. Okay, I will skip it. You just work. Proof is trivial. And one more proof of the Poincare inequality. Let me just state proof of immediate now. It's a special case, Poincare Vertinger. It's you just take V equal to LP and you define pi U is equal to U bar. That is all. Okay. Pi U equal to U bar is the average 1 over mod omega integral over omega U. Okay. That is it. It follows from that. You just apply that one. So you basically gives you norm of u minus u bar. Okay. And look at here, it has to fix it, right. So, pi is a mapping from basically W1P to L2, you see. And what is your P0? Your P0 is nothing but real line. And if u is equal to C is a constant, your pi u is nothing but u. That is it. This is the one you have to check it, because u is a constant, it will comes out, it is u bar equal to u. Okay. U equal to u bar, it is that constant. So, it follows. There is one more inequality in case I will not state now here, it is a time only if I have time to do the what do you say, it is called a Cones inequality. So, if I have time to do an elasticity system, I will do it, because you have to prove some positive definites Cones inequality. It is not difficult to test it, but let me not do it if we can do for elasticity systems, because so when you study PDE, end of it you have to prove the ellipticity, but in systems all the derivatives may not be appearing. So, you have to estimate that estimates in terms of the full estimate. You have to show that the PDE to prove is basically to prove a PDE is elliptic, the combination of derivatives appearing should give you all the derivative, essentially you should get the information about that one. So, with this I will stop here, and now we will move on to the weak formulation from next lecture onwards. Thank you very much.